Okay, good morning, everybody. So today's lecture, there's a tiny bit of history. I never ask you about the history, so this is mostly for interest rather than test purposes. And then I'm going to describe a little bit about the file system that's used in, well, Linux and Unix. Because everything in when you're using a command line interface in the Unix or Linux or on your Mac, all the information is coming from files. And so files are considered a fundamental component of the operating system. So it's kind of important that you understand exactly what does Linux or Unix mean, what exactly is a file to Linux or Unix, so that you can use them, read them, write them, and do things with them. Oh, if you want to, you can play Pac-Man in your console. It's not the greatest version of Pac-Man. If you don't know what Pac-Man is, Pac-Man's an old arcade game from when I was a kid. You might have seen it. But you can surprisingly play this in your console. Again, this is really strange that you can do this. The console was never designed to do something like an animation, right? It's meant, you type something, you press enter, something comes out. It's not meant to, you're not supposed to be able to go back somewhere in the console, change the appearance of something, and then come back to the command line prompt again. So the fact that you can do this is kind of surprising. Anyway, I'm not going to play it here. Okay, so what the heck is Linux? So Linux, everybody just says Linux, but really when people say Linux, they mean this thing called GNU Linux. So Linux is what's called the kernel of the operating system. And the kernel is the part of your operating system that provides the interface between hardware and software. So in that picture I showed you the other day, it's that box that's the second from the bottom, right? It's the part that talks to your hardware. There's other parts of the operating system as well that don't necessarily talk to the hardware, right? So there's a whole set of tools, the command line tools that I've showed you, that are normally considered part of the operating system. So that forms the GNU part of things. All right, so Linux is actually modeled on this thing called Unix. So often in this course, I'm going to say Unix or Linux. For our purposes, they mean the exact same thing. Unix was an operating system that was developed back in the late 1970s, although work started on it earlier than that. Right, if you're interested in the history of Unix, you can click on that link and see and read a little bit about it. If you read that article, you might recognize things that are still common today. Right? And so especially when you're programming in Python or in Java and you're wondering why do they do things like this, some of them come from the fact that Unix did these sort of things 50 years ago. Right? And so a lot of the issues that we run into, well, a lot of the features and issues that we run into with computing today, they all have roots back in the 70s. Okay, so why is Unix important? So Unix is important because way back in the 70s, there wasn't, if you want to buy a computer, you wouldn't buy something that sat on your desk, right? You would buy something that occupied an entire room. And the number of computer manufacturers, so there wasn't just AMD and Intel back then. A whole bunch of different companies would make their own version of their computers, and they would all ship their own version of an operating system, which you had to buy separately. And so if you learn how to work on one computer and you try to go to another computer, it'd be a completely different experience. And so Unix was the first portable operating system. So portable means you can take it, write it for one computer, take it with some modification, run it on another computer. And so you now got this idea where all computers can use the same operating system. The problem is this is way too expensive for individual users. So it's very expensive even today to buy a Unix license. Right. So that was in the 70s. So work's progressing to make this operating system. Roughly 10 years later, maybe 15, Richard Stallman, who some of you may have heard of before, created the GNU project. And so his idea was, I don't want to pay for this operating system. Well, people shouldn't pay for the operating system, right? Computing ought to be free. And so he decided he wanted to make a free Unix-like operating system. Unix-like because Unix is the dominant operating system at the time, right? If you want more people to use a computer, they should be using an operating system that's familiar to them, right? Around this time, there are other computers, so personal computers are starting to come into, are starting to become a reality. but they still all had their own different operating systems. Right? Anybody seen a Commodore 64 or a VIC-20 or a TRS-80? Yeah, so there's like one or two of you. So I learned how to program on a VIC-20 and a TRS-80 and a Commodore 64. That was a long time ago. You don't really see these things around anymore, except in a museum. Right? Okay, so he decided, I want to make an operating system. Now, to make an operating system, you need all sorts of other stuff too, right? You need a compiler so that you can write code so that your operating system can actually run. Right? And so they started development on the tool set, but they didn't really work on the kernel. So the kernel that eventually came into existence is called Herd, but its development was very slow. And in fact, it's only fairly recently where Herd was actually released. So it took them like 30 or 40 years before they had a functional kernel for their operating system. All right, so 10 years go by. They're still chugging away on GNU. And then this guy named Linus, he's a Finnish graduate student. So he was a master's student at the time. Around 1990, so CPUs are starting to become available to consumers, or more available to consumers, sorry. And so there's this thing called the 8386. So this is a famous CPU made by Intel, who obviously is still around today. And he decided, hey, I don't want to use Windows or DOS back then. I want a free operating system, right? And he's going to do it as a hobby. He asked for volunteers. Anybody want to help, right? And he decided to make a clone of Unix of the kernel, but he didn't have the tools. Fortunately, 10 years ago, GNU actually started creating the tools, so there was now a freely available compiler that Linus could use. And so he took the tooling from GNU, wrote the kernel. GNU said, hey, you've got a kernel that's working great. We'll mash these together, and thus GNU Linux was born. Right? And so the version of Linux that you're using on your computers now is basically this combination of GNU and Linux. Right? GNU for the tooling, Linux for the kernel. Everybody just calls it Linux. Right? Okay, so where is Linux used today? So it is the dominant operating system in cloud infrastructure and supercomputing, right? So anybody running a giant server farm is almost certainly running Linux, right? Why? Because a giant server farm might have 1,000, 10,000, 20,000 computers. You don't want to pay a Microsoft or Mac license for every computer, right? $100 per computer, that adds up to a lot of money. Linux is free. So you can now actually build these things for much cheaper than if you had to pay for an operating system license. Right? It is absolutely dominant in the basically the stuff that runs the internet. Right? Android is a derivative of Linux, and it runs on 70% of smartphones in the world. Much lower fraction in North America because a lot of people use Mac or Apples in the iPhones in North America. But worldwide, 70% of smartphones run Android. It's common in embedded systems. So again, things like those cameras that are up there, the Wi-Fi routers up there, there's a good possibility that they're running some kind of, some version of Linux. It's very uncommon on the desktop. So roughly 5% of desktop computers use Linux. That number goes up and down a little bit every year. Every time it goes up by like 0.5%, the Linux people say, yay, right? Now 4.5% of users are using it, yay, right? It's very small on the desktop. If you do a lot of development though, software development, or if you're doing a lot of research stuff, Linux is pretty easy to use. Now with the rise of Mac, or the fact that Mac is common everywhere and more or less, it's not exactly compatible with Linux, but it's pretty close. Macs are becoming more common too in that world. Google has this thing called Chrome OS that they use on Chromebooks. So these are inexpensive laptops that are often given to schools for discounted pricing or free. So their Chrome OS is based on Linux. If you count Chrome OS, the desktop percentage is actually quite high. A lot of kids running around who have grown up on Chrome OS. Okay, so the fact that we are teaching you or making you use Linux is in fact useful for employment purposes. Right. All right, you might occasionally see this term called POSIX, which kind of looks like Unix and Linux, right? POSIX is the Portable Operating System Interface. So basically a bunch of people got together back in the early days of computing and said, hey, look, we got all these different types of computers, but they can't work with one another. This is a real pain in the butt. Maybe we can come up with some agreement so that operating systems can have some level of compatibility, right? And so they cooked up this set of standards that define what a POSIX-compliant operating system ought to look like. And so Unix is one of these POSIX certified operating systems. Mac OS is also POSIX certified, so that's nice. Linux is not, but it's very close. So it's mostly compliant to this thing called POSIX. Windows is its own thing, right? All right, so there's a very quick history of the tooling that we're going to be using in the course. Let's see, just go back here quickly. Okay, so the GNU tools that we're using in the course, one of them will be the compiler for C when we get to that part. Most of the commands that you use on your in a Linux computer are going to or will have roots from the GNU project. And of course, the operating system itself will be using Linux. Unless you're on a Mac, and then you'll be using something else. Mac is, I forget now what it's derived from. I can never remember what it's derived from. But Mac is derived from an older version of Unix. So the operating systems that you're using today, with the exception of Windows, they all have roots back in the 70s. Okay, so what is this thing called Bash? Right, so this is the main focus of the first 5 weeks of the course. So Bash is the software that runs in what's called a terminal. Okay, so you may see this term called terminal, right? In Windows, there's even a program called terminal, right? When you run the program, you get a black screen that looks like that, and it looks like you can type stuff into the screen, into that terminal, and press enter, and something will happen, right? If I have one here, that's a terminal, right? It's a virtual terminal, so it's a terminal emulation program, right? Originally is not correct. In the very, very early days of computing, there's no keyboard or screen, right? The way you would get, the way you would program a computer, well, in the very, very early days is you'd have to take wires and hook them up into different places. Then they had punch cards, which is basically a piece of paper. You'd punch holes in it, feed that into the punch card reader, and the computer would interpret that as some sort of set of commands. Eventually, we got around to making a keyboard and a display. And so a terminal is an electronic or an electromechanical device for input or output, right? So there's here is a very old terminal, right? You can see it's got a keyboard, right? Now, if you look at this thing, I don't know if any of you have seen a typewriter. This kind of looks like a typewriter. That's a keyboard. You would type commands into the keyboard, and then if the computer produced some output, it would print the output here. So you'd get a piece of paper that comes out, and that would be your output to your program, right? A little while later, we hooked up a screen to the keyboard, and so now you can actually see your output on the electronic display, right? And so these things still exist. They no longer look like this. They're software programs. They're called terminal emulators, right? And so again, there is a terminal emulator, right? You can type commands into the emulator, right? And something happens. Now the question is how is it that something is happening, right? So yes, I can type that in, right? So that's the keyboard, right? But there has to be something that interprets what it is I'm typing in, and that's called the shell, right? And so shell is just a software program. Typically it runs in a terminal, doesn't always, right? But it often runs in a terminal, and it interprets the text to determine meaning, right? So when I type in something into my terminal, right, and press enter, it's the shell that gets the terminal output, so the ls, right, and tries to interpret that as a command, right? So it interprets text. Where is the text coming from? It's coming from the terminal, right? And there are a whole bunch of different shells, right? And so there's a shell called sh, short for shell, right? That's the shell that we're using in the course is called bash. There are, on the Mac, if you use a Mac and you ever open up your terminal program, it's using a shell called the Z shell. There's a C shell, there's a T shell, there's a TC shell, and there's lots and lots and lots and lots of other shells, right? One of the problems of having a free operating system is that anybody can write their own software, and so lots of different people have written shells. Oh, there's a K shell as well. K shell's pretty famous too. So if you click on that link there, you can see a bunch of different shells, all in use. Most of them still in use today, and you can see you can compare them for their features, right? And Windows has its own version of a shell, right? So Windows has PowerShell and its own terminal program. The interesting thing about Windows is that its shell works very differently than the Unix shell. So there is a fundamental design difference between the Windows shell and the Unix shell. If you're interested in that, just do a quick internet search and you'll see, you'll come across lots of information that explains the differences. The shell we're using in the course is Bash. Now this is important because if you're on a Mac and you start up, you open up your terminal and you start to do your work, you're actually working in the Z shell. So the Z shell is different than Bash. The commands that it has built into it are different than the ones that are built into Bash. So you have to be careful if you're working in Mac, right? It would be, you might want to switch your shell to Bash when you're doing the assignment. If you close the terminal and open it up again, it'll pop back up into your original Z shell. So you don't have to worry about making any permanent changes, right? Bash stands for the born again shell because it replaces the older Unix Bourne shell, which is named for its creator Bourne. I can't remember what the first name of this person was. Anyway, Bash is the most common login shell for Linux distributions, but it's not guaranteed to be the one, right? So if you jump onto someone's Linux computer, it may not be Bash, right? It could be something else. But most Linux distributions, especially like Ubuntu or the common ones that are meant for widespread use, they probably start out with Bash. Mac used to use Bash until 2019. Then they decided to change things, broke a whole bunch of stuff, and it's now Z shell. Right? It broke a bunch of stuff because lots of people had a whole bunch of scripts written for Bash, and then suddenly they switched to the Z shell, and now your scripts that used to work in Bash don't work the same way, or they don't work at all in the Z shell. Right? So be careful if you're on a Mac. I think for the most part, by now, I've gotten the assignments to the point where it doesn't really matter, but be aware that there could be an issue. When the TAs mark your assignments, they're going to be marking it in Bash. Okay, so that's the shell and the terminal. Now, what about the file system? Okay, so if you click on this link here, this is written by a guy named Eric Raymond, who did a lot of the early development of Unix and the C programming language. So this is the, what the heck is it called? The Tao of Unix Programming, I believe is what the name of the book. If you're interested in the history of things and why things work the way they do today, this is a very interesting book. If you're not so much interested in that thing and those sort of things, this is a less interesting book. All right, so what is the file system? So the file system is the part of the operating system that controls how data is stored and retrieved. Right? So you're working on your computer in a terminal, right? All the information that you have available to you, I shouldn't say all, much of the information that you have available to you is in the form of a file, right? There's some information stored somewhere, right? Probably on a disk still today in a modern, well, not a disk, sorry, a solid state drive on most of your laptops, right? Some of you might have a disk drive still, perhaps on your desktop, although almost everybody has an SSD now. You might be stored on a USB drive, right? Optical media. Do you guys even know what a CD is? Yes? Yeah, okay, good. So this is funny because you don't really see them anymore, right? Which is kind of hilarious. I mean, in my lifetime they appeared and that was revolutionary, right? And now they're almost gone. Magnetic tape. Anybody seen a cassette tape? Yes? Okay. So it used to be, so back when I was learning how to program, if you wanted to store something, you would pull out a cassette tape, stick it into a little cassette reader that's plugged into your computer, and that's how you would store information. Right? It'd be on the same sort of cassette that you'd use to play music, which you no longer see anymore either. Right? As far as I know, no one used vinyl. So I mean, someone might have, but it wasn't common. It's definitely not common. Magnetic tape is still used. Except it doesn't look like a cassette. They look like giant wheels, and there's a ribbon of magnetic tape. They're still used to back up large amounts of data, and so many of the servers or server farms that have to back up lots and lots of information. There's a separate backup site connected by a network. In that backup site, there are giant machines consisting of a bunch of magnetic tape. All right, so file system, how do I access and store data in a quote-unquote permanent way? Right? There are many, many kinds of file systems. Right? Windows, it's common that there are 3 on a modern Windows system. There's actually a 4th called DOS, which is pretty uncommon. Right? So FAT, exFAT, and TFS. Right? FAT and exFAT are probably how your USB keys are formatted. So they probably use these file systems. Right? NTFS is the, I guess it's the more modern version of a Windows file system, although it's very old at this point now too. Mac OS, they have their own file system called the, not surprisingly, Apple file system. Right? Linux has a whole host of file systems. Right? There's dozens. Right? ext, ext2, ext3, ext4. Most of your computers, most installations like Ubuntu or something like that, something that's easy for people to use, probably use ext or ext4. There is a file system called RiserFS, although this isn't being used so much because Riser is in jail. XFS is another common operating system, common file system, and there's many, 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 many other file systems. Right? Lots and lots and lots of different file systems. All right, now common to all of the Linux file systems is this notion of a device. Right? So the device corresponds to a physical piece of hardware that can store files. Right? So it would be your solid state drive or your floppy disk, or your disk drive, USB flash drive, right? Something like that that can store information. Right? Okay, so on that device, there are these things, each device on a Linux system actually corresponds to a file in Linux. Right? And so the way that Linux communicates with your file system hardware is through a file. Right? And so it's a special file called a device special file. But what that means is that if you are writing a Linux application and you want to store information to your disk, right? All you do is you open up this thing called a file, you write information to the file, close the file, and that information magically gets stored on your hardware. Right? And so in Linux, Linux or Unix, you'll often see the phrase, everything's just a file. Right? And this is what it is alluding to. Right? Whenever you are, a lot of input and output on Linux or Unix can just be thought of as reading or writing from a file. Okay, so a device special file is just an interface, right? So it looks like a file, but in actuality it's something else, right? The operating system takes care of all of the magic of writing to your hardware for you. Right? This is nice, right? You don't want to have to know exactly how your hard drive works in order to store data, right? You don't want to have to go and look at the hard drive manufacturer's API, if they have one, right? In order to save a file, right? The operating system abstracts all of that for you, right? And so that makes it very easy to read and write information, right? Regardless of the device, right? So it doesn't matter if it's a disk, it doesn't matter if it's a solid state drive, it doesn't matter if it's the network, right? This all just magically works. Okay, so what the heck's a file, right? Now, most of you are familiar with the idea of a file, right? You've got a Word document, right? That's stored as a file somewhere on your disk, right? You double-click assignment1.docx, right? And Word opens up your Word file, right? So the contents of a file, it's just information, right? And it's digital information, so it's binary. So your file is just a bunch of ones and zeros. That's all it is, right? So how do we store the ones and zeros on a disk or on a device, right? So the way it actually works is extremely complicated, right? And it's different for every kind of device. So we're going to simplify things in an enormous amount, right? And we're going to imagine that our operating system simply says, hey, my disk drive is just an array, and you all know how to use an array. Right? So if I have, how many? 1, 2, 3, 4, 5. Okay, so here's a picture of a device that has 5 files on it. Right? Remember, this is just an array. So my first file is the red one. Right? It occupies the position in the array, 0, 1, 2, 3, 4, 5, up to whatever this position is here. Right? Then my green file, the green block corresponds to another file. Right? So it occupies position, I don't know, say 101, 102, 103, up to 400, say. Right? And so on, and so on, and so on. Right? Now this is a gross, I mean, it's such a huge simplification that it's completely wrong. Right? But this is a good way to think about it. Right? A file, right, is just a contiguous, you can think of it as just being a chunk of zeros and ones, right? It's stored on your disk somehow, not this way, but somehow, right? And your operating system provides the illusion that it is in fact stored on your disk in this way, right? I can read the first bit of information, then the second bit, then the third bit, and so on and so on and so forth, right? Okay, so for your operating system to actually store your files, it needs to know some information, right? So to store and to retrieve information about a file, right, your operating system needs to know some stuff, right? So there's a couple of obvious things that it needs to know, right? So suppose I want to get information from the blue file, right? What is the one obvious piece of information that you need to know, right? So I want to get the 10th bit from the blue file. Right? So what would I need to do, assuming this is just an array? Yes? Where it starts. Yeah, you need to know where it starts, right? I need to know what is the starting location of the file, right? And there's a bunch of other information that might be useful as far as files go, right? How big is the file, right? And a bunch of other stuff, right? And so in Unix and in Linux, right, files are stored using this thing called an inode, right? An inode is just a data structure. Right? A data structure that stores information about the contents of a file, right? So for example, which device is this file on, right? Is it on your hard drive? Is it on your SSD drive? Is it on your USB drive, right? It stores information about the kind of file that it is, right? In Linux and Unix, it stores information about who owns the file, how big is the file, right? And a bunch of other stuff, right? When was the file created? When was it modified? When was it accessed, right? Now there's something missing from this list. Does anybody see what's missing from the list? That you would think ought to be here? Anybody? Anybody? Yes? Is it permissions? Those are missing in fact, but those are stored somewhere. But that's not the thing. Yes? Yeah, what the heck is the name of the file, right? You would think that would be one of the things that would be stored about the file, right? Because that's the way that the typical user is going to access the file. I want assignment1.docx, right? Or I want, I don't know, mysys124.java or something like that, right? Okay, so we'll come to that in just a second, right? So an inode is just, every inode has an integer number called its number, right? And so that number is unique for all inodes on a device, right? So on your USB key, right, assuming it's formatted in some sort of Linux file system, right, all of the inodes on that USB key will be, that belong to that USB key will be unique, right? Now the inode numbers are not unique across devices. So you can have inode number 12 on one device and you can have inode number 12 on a second device, right? So the devices are kept separately. So back to this issue, where the heck are the file names? Right? And so it turns out the file names aren't stored in the inodes in Linux or Unix, right? Instead, they're stored in this thing called a directory, which you know as a folder. Most of you will know as a folder, right? So in Windows or in Mac, you double click on your little thing that looks like a file folder, right? That corresponds to what is called a directory in Unix or Linux, right? So what the heck's a directory? It turns out in Unix, it's just a file, right? So a directory itself is a file, right? The file, it contains information. It's basically a table, right? So in the first column of a directory file, you can think of that as storing an inode number, right? And in the second column, you can think of that as storing a file name, right? So a directory is just a file that maps file names back to inode numbers. So for example, I might have some directory. This is the directory that contains the Jupyter notebook for the Bash notebooks, right? So on my computer, there might be another directory called images, right? And that contains a bunch of image files for the notebooks, right? There's another directory called scripts, and that contains all of the bash scripts for the notebooks, right? There's a regular file called animals.txt, right? So if you remember back from the previous lecture, animals.txt has 4 lines in it. It's got the names of some animals, so on and so on and so forth, right? And so the directory tells you, or tells the file system, sorry, the operating system, right? Where, if the user is using this file name, what inode number does that file name actually correspond to? Right, so your file names are not stored in the inodes themselves, they're stored in this thing called the directory. Okay, so what's a hard link? So a hard link is, a hard link is a directory entry that maps a file name to a file. So for our purposes, you can think of a hard link as being one row of the directory. Right? So maps file name to a file, which is just an inode, right? So for a file to exist, it must have a hard link, right? So in order for your operating system to know about the file, right, it needs to know the name of the file and what inode it corresponds to. Therefore, it needs a hard link, right? And that table on the previous slide simply shows the hard links for the files in the directory containing my notebooks, right? Now, it turns out in an operating system like Linux or Unix, right, you can make multiple hard links to the same file, right? So back here, right, I've got a file called animals.txt, and it points at this inode number 662411. It's possible for me to create another hard link that has a different name. So more animals.txt, and it points at the same inode, right? So it also points at 662411, right? So if you have 2 different names that point to the same inode number, right? That's just like in Python and Java when you've got 2 variables that refer to the same object, right? It doesn't matter which variable you use to change the object or to ask the object to do something, right? It's the same object that does the something, right? So if you have multiple names that all point to the same file, it doesn't matter which file name you use to access the contents or to modify the contents of the file, right? Either the contents of the file, you can read it or write to it, right? If you now use a different name to access the same file, right, it also sees the changes that were made, right? So the notebooks go into more detail in how you can actually do this. I'm not going to do it here. I'm not going to ask you to do it on assignment, right? If you're interested in how you do this, look in the notebook and look at the ln command, right? Okay, what time do we have? Sorry. 10:04. All right, this wants me to go to the file system notebook and continue from the section titled File System Hierarchy Standards. Sure, let's do that. Start here. Okay, so table of contents, Linux file system. Oh, if you want to read more about the history of Unix and Linux and some of the philosophy underlying the design decisions of Unix, you can read those 2 notebooks. Okay, so this wants me to go to, so notice that everything that I've talked about in the lecture, it's going to be in the notebook, probably in some sort of expanded form, right? So there's something that you forget or are unclear about, you can go back to the notebook and refer to it back and refer to the information back here. Here's the information about hard links, right? The slide wants me to go here. And so when you're using an operating system, when you're using Unix or Linux, sorry, I think, yes, Unix or Linux, right? Most, but not all, of these operating systems, their file system is set up in a particular way. There's no guarantee that they are set up in this particular way, but the chances are very good that they are set up in this way. So there is a standard that is not, I mean, it's called the standard, so it defines how your file system should be set up. But there's no requirement that your operating system actually follow this standard, right? So the hierarchy standard defines the directory structure that are common, that a Linux distribution might want to follow, right? Mac OS has its own standard, but because Apple controls the operating system, right, the fact that there's a standard form isn't so important, right? Nobody else is making another operating system for Mac, so they have full control over it. So it's similar, but it's different. Right? Now, you don't actually need to know all of the gory details about the standard, but it is very useful to know something about how a typical Linux file system is laid out. Right? Okay, so the one thing that is true is that there is always an uppermost directory called /. So this is the /, right? Every year, like 20 students will use the other /, the backwards /, right? It's the /. The backward / means something else, right? So the / is the directory that contains all other directories, right? And files. So that is called, it's called the root directory, right? It's often called / or just root, right? Root's a bit confusing because there's also a root user. Never mind, right? It's called the root or / directory. All right, so if you're in a terminal, you can switch to that directory, right? So I can go into the uppermost directory of the file system. The way you change directories, oh, sorry. So when you open up so I've got a terminal here with a shell running, right? So when you open up this, when you open up your terminal and your shell starts running, the shell will start running in what's called the user's home directory, right? So if I want to know what is the user home directory on my computer. Oh, sorry, this isn't the home directories. Hang on. There we go. Okay, so on my particular computer, right? When I start up an interactive shell, it starts out in the directory root, right? Oh, sorry, root. Then there's another directory inside the root directory called home, right? And inside the home directory, there is another directory called Burton, right? So I'm currently in the directory root home Burton, right? Anytime you see a / inside, this is called a path name, right? If you see a /, right, that is a directory separator, right? Unless it starts at the beginning, in which case it's root, right? Anywhere else, it separates two different directory names, right? So that / there separates home and Burton. So you know that there's 1, 2, 3 directories in this particular path name, right? Okay, so my shell is currently in the home directory, my home directory. If I want to go to the root directory, I can use this command called cd. So cd changes the current working directory, right? The working directory is just the directory that the shell is currently in, right? So cd space and then / switches to the root directory. Notice it doesn't produce any output. So if you do it here, cd root, no output. So this is one of the design philosophies in the Unix operating system, right? If a command has nothing useful to say, it should say nothing, right? So if you want to switch to an existing directory, right, the command simply switches to that directory and then doesn't tell you anything, right? Produces no output, right? So many commands that you use in Linux or Unix will often produce no output, right? They'll do something, but there's no output displayed to you, right? So for example, many beginning programmers, had they implemented cd, would have said, switch directories to root, right? That's not the Unix philosophy, right? Unix philosophy says, do not say nothing if there's nothing important to say. So we're now in the root directory. pwd means is the command that prints the working directory, right? So if you run that command there, it tells you your shell is currently in the root directory, right? So cd, change directory, pwd, print the working directory. And that's right there, right? If you want to know what files are in a directory or in the current working directory, that's ls, right? List the files and list the files that are in the current working directory, right? So I'm going to switch to root. Oh, sorry, I already switched to root. Okay, I'm now going to list the contents of that directory, right? And you see that there's a bunch of files sitting here. They're even color-coded. The color coding depends on how your shell is set up, right? So anything shown in blue or green corresponds to a directory here. Anything in blue is a directory. Anything in green is something called a link. But for our purposes right now, they're just directories. And so you can see there's a bunch of directories in the root directory, right? And if we go back to this link up here that I should have opened earlier, right? The file system hierarchy, what the heck is that? Sorry. The file system hierarchy standard says, if I can, sorry, I've got a busted control key, so there we go. Is there a picture? Oh, here we go. Okay, so the file system hierarchy standard says every Linux file system should have a root directory, right? Inside the root directory, there should be something called bin, something called boot, something called dev, something called etc, and so on and so on and so on and so forth, right? Notice that in etc there should be something called opt, right? And a bunch of other stuff as well, right? Again, it's not really important that you memorize all this, right? But it is useful to know there is something called home, because that's where your home directory is probably, not necessarily, but probably located, right? So home directories by default end up in this directory called root. So the directories belonging to individual users belong in this directory called, are typically found in this directory called home, right? And there's a bunch of other things here as well, right? Again, not super important for the purposes of this course. It's useful for you to know that these directories exist. Okay, so when you see things like user and boot and dev and etc and home, right, these are all directories that are part of this hierarchy standard. All right, so these commands that I've been using, so ls, pwd, and cd, right, these correspond to commands. Right, now in Unix or Linux, right, there are different kinds of commands. So there are commands that the shell are built into the shell, right? And so these are called the built-in shell commands, right? And then there are other commands, right? So the other commands, they're not part of the shell itself, right? But rather they correspond to, they probably correspond to programs that are somewhere on your file system, right? So the built-in commands are commands that are defined by the bash shell. Other commands are just programs that can be run by the bash shell, right? Now, you may need to get information about a command, right? So if you want to get information about a command from the terminal, you can. There's lots of different ways to do it. One way to do it is to use this command called man, which is short for manual, right? So if we type man built-ins, right, you get a you get an awful looking listing. Man built-ins, better, right? This tells you all of the commands that bash is natively aware of, right? So there's cd, right? pwd is here somewhere. Yes, there it is, right? And there's a bunch, well, a not terribly long list of other commands, right? So cd, pwd, these are commands that the shell knows how to, can perform on its own. Right. Quit that for now. Later on, I'm going to tell you how to use the man pages in a, produces a lot of output, sorry. That's a lot of output, hang on. Cell, clear, thank you. Okay, there we go. Right, instead of using man, there's a command called help. Right, so if you use help, help is a built-in command, so the shell knows about it. Help lets you find information about built-in commands. So if you type help cd, it gives you back some information on how to use cd. Right, oh, again, spits out a lot of information, sorry. I'm just going to clear this. Oh, come on. Okay. Right, and similarly, you can ask for help for pwd, right? And it'll give you a little synopsis of how to use the command. Now, these are meant to be, these are not meant to be tutorials, right? So if you use man or help, right, you get information about the command. So basically, you get told what does the command do, how do you use the command, but it doesn't give you any examples or anything like that. Right? Typically, does not give you any examples. Right? If you need examples or something like that, you've got the notebooks, you've got the lectures, you've got the internet, which is probably, frankly, the easiest way to find information about these commands if you want to know more about them. Right? All right, so ls is not a built-in command. Right? So again, if we do man built-ins, we look for ls in this list up here. It's not here, right? So it turns out ls is a program that runs, is a program that's part of the GNU set of tools, right? So if you want help on ls, right, if you try that, that doesn't work, right? So remember, help only gives you help for the built-in commands, but there is a man page for it, right? So the command man space ls asks for the manual page for the ls command, right? And now you get information about this. Later on, I think I'm going to show you how to read this man page. For now, I'm just telling you that this thing exists. Okay. All right, so a very incomplete image of the directory structure that's described by the hierarchy standard is this, right? So well, even in Mac and in Windows and in Unix, right? The file systems that you are used to looking at, they are hierarchical, right? So if you're a Windows user, you know that there's probably a C drive, right? And in that C drive, there's, what the heck's it called? It's called users, right? There's a folder called users. In the users folder, there's a directory that corresponds to your user account, right? And then in your user account, there's another folder, documents, and things like that, right? So most of these file systems are organized in a hierarchical fashion, right? So in Unix, the directory at the top is root. Underneath that directory, there's a bunch of other directories, right? One of them is home. Inside home is probably your user directory, right? So there's a brief description of the individual directories. Again, not super important that you actually know what all of these are, right? Useful to know that there is a root home directory, right? Okay, so a little bit more about ls. So ls doesn't just list information about about the current directory. You can use ls to list information about any file. Right. So where am I right now? So I'm in the root directory. Right. If I type ls, I get all the files in the root directory. Right. If I'm in the root directory and I type ls bin, that will list all the files in the directory called bin that is in the root directory. Right, so blah, there it is. Right, bin turns out to hold, it holds the commands or the programs corresponding to many but not all of the standard commands that come part of your distribution. Right. Now, if I'm in a different directory, so I'm now in my home directory, and I would like to know information what's in the bin directory, right? You can always get the information from that directory by typing in ls, and then you have to tell it which bin directory do you mean? I mean the one that's in the root directory, named bin, right? And that will produce the exact same output as before, right? And so in the next lecture, I will tell you about absolute and relative path names. We're out of time, so we'll pick this back up, I guess, next week.